Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called optimizing coal plant blending operations. To provide these services, HI is supported by its business partners, GAMS, IBM and TD SYNNEX, all of which are producers of artificial intelligence technologies. HI is a company at the forefront of high-performance artificial intelligence. In Chinese thermal power generation companies, the cost of purchasing fuel accounts for more than two-thirds of the total. In addition, the mixing of coal in thermal power plants has a major impact on damage to the plant's auxiliary equipment, as well as on soot and sulfur dioxide emissions. Therefore, the optimization of the fuel mix is of great importance to reduce production costs, in addition to contributing to energy conservation and emission reduction and promoting the sustainable development of the national economy. Optimization is critical to increasing operational efficiency and reducing emissions from the company's boilers. In Chinese thermal power generation companies, the cost of purchasing fuel accounts for more than two-thirds of the total. In addition, the mixing of coal in thermal power plants has a major impact on damage to the plant's auxiliary equipment, as well as on soot and sulfur dioxide emissions. Therefore, the optimization of the fuel mix is of great importance to reduce production costs, in addition to contributing to energy conservation and emission reduction and promoting the sustainable development of the national economy. Optimization is critical to increasing operational efficiency and reducing emissions from the company's boilers. The reference mentioned in the article is considered the key to this conference. Coal blending optimization for power plants with particle swarm algorithm. Using the technical indicators and coal quality characteristics, the optimization model determines the most suitable coal mix for the actual power plant situation. The table presents the characteristics of 7 types of coal used in the power plant. 6 characteristics are presented: Q net, VAR, R, C, SAR, and unit price. To meet a stable operating condition of 70%, the power plant must meet certain limits of the indicators for the chemical composition of the coal mixture. These are Q net greater than or equal to 15.903, 42.5 greater than or equal to VAR greater than or equal to 37, 35 greater than or equal to R, 20 greater than or equal to MAR, and SAR less than or equal to 1.5. The constraints are not direct on the primary variable xi, but a quadratic constraint on the derivative variable yi obtained after processing xi. Minimizing the price is the goal of the mathematical model. The table presents the results of 7 simulations. The mathematical model implemented is a particle swarm algorithm. The graphs present the evolution curve of the global optimal values of each coal type, in such a way that the solution is the one obtained in the last iteration, in green. Since the low calorific value of these types of coal is low, in order to meet the condition that the calorific value is greater than 15,903 MJ/kg, the coal to be used must be mixed. The optimal percentage of coal mixture is 0.05 for coal 1, 0.12 for 2, 36.0 for 3, 0.16 for 4, 63.36 for 5, 0.06 for 6, and 0.2 for 7. It should be noted that the actual planning of the coal mix should cover the planning horizon, which should consider variations in coal supply and expected demand for electricity generation. Another reported reference is presented in the article. A surrogate intelligent adaptive generation framework for cost-effective coal bending strategy in thermal power units. The paper proposes an adaptive method of condition classification, based on convolutional neural networks, which determines the probability distributions of the output, the coal mixing, and completes the interval division based on previous operational data.
La metodología se utilizó en la central térmica operada por Babcock and Wilcox Beijing Company Ltd, BAN-W. Se presenta el caso de una unidad de generación a carbón de 350 MW, realizado durante las importantes fluctuaciones del precio del carbón causadas por las condiciones internacionales en 2021 a 2022. El rendimiento de esta unidad se vio notablemente afectado, con un marcado aumento en los costos de generación.
The methodology was used at the thermal power plant operated by Babcock and Wilcox Beijing Company Limited, BANDL. The case relates to a 350 megawatts coal-fired generation unit, built during significant coal price fluctuations caused by international conditions between 2021 and 2022, and the performance of this unit was noticeably affected, with a notable increase in generation costs. To address this problem, a methodological framework for generating cost-effective coal blend system, CBS, is proposed. The methodology includes a unit recognition of output conditions, UOCR, module, which allows adaptive classification based on operational historical datasets, performing intelligent condition recognition with image classification models based on convolutional neural networks, using combination strategies and unit parameters as inputs. The generation of profitable strategies, SESG, module uses a surrogate model to assess the economic viability of strategies in terms of environmental and carbon costs, among other factors. The UOCR is also used as another surrogate model to validate the viability of the strategy. SESG are generated using a population-based metaheuristic algorithm. The UOCR achieved an average training accuracy of 96.64%, and the cost-effective strategies reduced costs by an average of 3.37%, compared to the strategies currently implemented. The name of this system is Imitator. The cost-effective strategy generation, CESG, module uses a surrogate model to assess the economic viability of strategies in terms of environmental and carbon costs, among other factors. UOCR is also used as another surrogate model to validate the feasibility of the strategy. The cost-effective strategy generation, CESG, module uses a surrogate model to assess the economic viability of strategies in terms of environmental and carbon costs, among other factors. UOCR is also used as another surrogate model to validate the feasibility of the strategy. Imitator is a novel neural network that transforms CBS and other inputs into dimensions compatible with carbon characteristics into image classification models, allowing pre-trained models to perform recognition of output conditions, carbon mixing, and resulting features. Imitator assimilates an input or output matrix to an image. This is true when you consider that images on a computer are stored in arrays of pixels. For Imitator, the characteristic matrix of coal is equivalent to an image. The input matrix is unit parameters resulting from several steps performed by CBS. Imitator is based on a combination of attention mechanisms and transposed convolution matrices that are used for feature extraction and input transformation. The result matches the common input dimensions required by pre-trained image classification models. Convolutional artificial neural networks, CAN, correspond to an artificial neural network, specialized in identifying certain types of patterns, such as images. CAN applies a set of convolutional filters to the input images. Each filter activates different characteristics of the images, allowing for faster and more effective training. Now, instead of images, we can have input and output matrices, from past coal mixing experiences, that relate the input parameters to the mixture created for the coal. The table shows the description of the data for the input parameters in the dataset. Classifying the unit output condition involves dividing the power of the generating unit into different ranges based on magnitude, while categorizing CBS and unit parameters. In this case, the operating range of the plant has been divided into 6 conditions, starting at 180 megawatts, and for each of them a separate model is calibrated. The graph shows the fit in the training and verification phases. The figure shows the comparison between the original empirical classification, I gray, and the adaptive classification, in multiple colors associated with the ranges. In the actual dataset, production was concentrated between 180.0 and 307.1 megawatts. In the theoretical and empirical dataset, the range extends to the capacity of the plant, which according to adaptive classification is not achievable. This failure in estimation will bring undesirable consequences, since plant operators can commit to supplying coal, which can theoretically be achieved, but the quality of the coal does not allow it. This can only be discovered using mathematical models. The adaptive method significantly improves the granularity of conditions, allowing for a higher level of refinement in CBS. The figure shows the exchange rate between the profitable AI-generated CBS and the original, mental model-based strategy. The results are presented for the 6 operating ranges of the unit, in terms of total cost, cost of coal and other costs. Band with strategy to define an intelligent, adaptable and cost-effective CBS, assisted by artificial substitutes, generates a methodological framework that reduces reliance on human expertise in decision-making, and significantly improves the economic efficiency of coal blending strategies. The CESG is designed with a surrogate-assisted model to comprehensively assess the cost-effectiveness of the strategy, impose constraints on production conditions, and coal quality requirements based on the UOKR, produce cost-effective CBS, and use meta-heuristic algorithms that, on average, reduce total cost by 3.37% and coal by 3.62%. The case: optimal blending of coal by linear programming for the power plant at Sytomyr coal mine is presented below. It uses a linear programming model to determine the optimal mix of coal in terms of quality and quantity. The coal, with different characteristics, is extracted from the Sytomyr mine and feeds the Sytomyr thermal power plant. A linear programming model is developed to determine the optimal coal mix in terms of quality and quantity. Coal with various characteristics is extracted from different panels in the lignite district of Sytomyr and fed to a nearby power plant. The quality of the coal is extremely variable through the horizontal and vertical directions, which entails the precise planning of coal blending during the mining and stockpiling stages. The objective is to match the calorific values required by the plant. A large penalty must be paid to the plant if the technical condition is not met. The quality features and production capacities of coal from different panels are determined and are used in quality constraints. The power plant requires coal in 2 groups, which are of different qualities and quantities. Therefore, 2 linear programming models complementing each other are developed to determine the blending conditions that satisfy the needs of the plant. Reasonable solutions are obtained and optimal amounts of blending are handled. The model also allows the evaluation of coal panels of low quality. Sytomyr Coal Enterprise, SCE, is an open-pit mine operating in Turkey, 20 kilometers northeast of the city of Kütahya. The company has problems with the quality and quantity of coal supply to the plant. To overcome these difficulties, it was necessary to design a well-planned and organized mixing operation, with a corresponding production plan. Several reasonable solutions were found using the linear programming model. The Sytomyr thermal power plant has 4 combustion units. The plant's annual coal need is 6 million tons. The first 3 combustion units need 45 million tons, while the last unit requires 15 million tons. Failure to meet the quality and quantity of coal required by SCE may result in penalties for the coal company or a decrease in the efficiency of the power plant. The blending requirements of the coal are as follows. Coal coming from the processing plants, fine coal, and that produced from the stock of Kizik, stock of Marl. The B3 level, B2 level and B level can supply Unit 1, Unit 2 and Unit 3. Coal produced from the stock of Kizik, stock of Marl and B3 level can supply Unit 4. Coal quality varies greatly in the horizontal and vertical directions of the mine, so good coal mixing planning is required during the mining and storage stages. A bad mix means that a fine must be paid to the power plant. The objective of the model is to adjust the caloric values ordered by the plant. The quality characteristics and production capacities of coal are determined from different blocks that are used in quality restrictions. Supply and demand conditions are also used to determine related constraints. The plant requires coal in two groups that have different qualities and quantities. The models get reasonable solutions and produce optimal amounts of mixing. The model also provides the evaluation of low-quality coal blocks. They was solved in the Lindo optimization platform. The blending requirements of the coal are as follows. Coal coming from the processing plants, fine coal, and that produced from the stock of Kizik, stock of Marl. The B3 level, B2 level and B level can supply Unit 1, Unit 2 and Unit 3. Coal produced from the stock of Kizik, stock of Marl and B3 level can supply Unit 4. The two different linear models were developed since there are two design specifications in the power plant. Therefore, first, the amount of coal of the B3 level and stock of KZK are determined for Unit 4 with the help of the first linear program, and then the rest of the determined amounts are used in the second linear program developed for Unit 1, Unit 2 and Unit 3. After determining these conditions, the main aim is to obtain coal blends that have the maximum heating calorific value in the range of specifications requirements of the coal. In Seatomer coal mine, 6 different coal types produced from different panels and levels are treated. The terms for these coals, their average calorific values and annual quantity to be extracted according to ideal planning are shown in the table. These coals need to be blended in accordance with the specifications required by the power plant's burning units. Seatomer power plant has 4 burning units. The operating conditions of these units are shown in the table. The annual coal requirement of the power plant is 6 millions of tons. The first 3 burning units, Unit 1 to Unit 3, with the same requirements, need 4.5 millions of tons, while the last burning unit, Unit 4, requires 1.5 millions of tons. According to the mathematical model, it was possible to make the most of the resource from the coal quarries. 175 million tons of coal from the B3 quarry were used. This quarry contains low-quality coal, which was used in mixing processes rather than being treated as waste material. This led to better use of the best quality coals. As can be seen in the table, the quality of the mixed coal is 1721.8 kilocalories/kg. This value is within the caloric value range of Unit 1, Unit 2 and Unit 3. If the results of these tables are considered together, the production targets are achieved. All science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.